All right, so yeah, so like I said, 40 and 42 are the first two that I've got in chat. Give me 1 second to get the assignment
Wasn't
pulled
there one
up.
that we were supposed to do yesterday, but we ran out of time?
Okay. All right, so 40 is this one. Okay, so the one I've got for 40 says evaluate the integral x squared plus 1 over x minus 10 x minus 9 squared. Okay, so this is a partial fractions problem because the denominator is factored already. And so for partial fractions to work, we need really two conditions to be satisfied. One is the denominator needs to be able to factor, and two is the degree of the numerator needs to be smaller than the degree of the denominator, which it is, because the degree of the numerator is 2, degree of the denominator is 3 if we were to multiply that out. So we're going to break this into partial fractions. Normally we have to factor the denominator ourselves, but it's already done here. So we get x squared plus 1 over x minus 10 and then x minus 9 squared. So we split that into a over x minus 10 plus b over x minus 9 plus c over x minus 9 squared. And the idea there is that this x minus 9 squared, that's what's called a repeated linear factor. And so when you have a power of a factor like that, every power from the biggest one down gets its own fraction. So if this had been x minus 9 to the 4th power, you'd have x minus 9 squared, x minus 9 to the 3rd, and x minus 9 to the 4th. And so you do every power from whatever the biggest one is down. And so here we've got 2, so we do x squared, or x minus 9 squared, and x minus 9 to the 1st. So now we're going to try to solve for a, b, and c. So let's do that down here. So we're going to multiply both sides by the common denominator, which is x minus 10 and then x minus 9 squared. And we want to think of that as being over 1. And the idea is that this multiplies to the left-hand and right-hand sides of the equation. So on the left-hand side, when you multiply that, the x minus 9 and the x minus 9 squared cancel. So you're left with just the numerator. So when we get that, we get x squared plus 1 on the left. On the right, on the first one, so on the right, this distributes to all three fractions. And so on the first fraction, the x minus 10 in the denominator cancels with the x minus 10 in the numerator. So you're left with a times x minus 9 squared. And then on the middle fraction, this x minus 9 cancels with one of these two x minus 9s. So we get b, and we get x minus 10 and one factor of x minus 9. So we get b times x minus 10 times x minus 9. And then on the third one, both x minus 9s factor, but the x minus 10 does not. So we get c times x minus 10. Does that make sense to everybody? Everybody good? Okay, so when we do that now, we distribute the right-hand side. So we're going to square x minus 9. That gets us x squared minus 18x plus 81. For the middle one, I'm going to multiply these out first. So we get like distribute or FOIL, however we want to call that. So x times x is x squared. And then we get minus 9x minus 10x, which is minus 19x. And then plus 90. And then we get plus cx minus 10c for the third set. So now we're going to distribute the a and distribute the b. Also the c. So all right, so 8ax squared minus 18ax plus 81a. And then we get bx squared minus 19bx plus 90b. I guess we already distributed c, so we get cx minus 10c over here. And now we want to combine like terms. So you combine all of the x squared terms. So we get a plus b, and that's it. Actually, my bad. A plus b x squared. And then for the x terms, we're going to get negative 18a minus 19b plus c times x. And then the constant terms, we get 81a plus 90b minus 10c for the constant terms. And so it might be good to kind of track those, make sure we got them right. So the x squared terms are coming from this one and this one. That gets us this. And then the x terms are coming from the negative 18ax, negative 19bx, positive cx. So that gets us this one. And then the constant terms are 81a plus 90b minus 10c, and that gets us this. So just to make sure we didn't miss anything, because there's lots of small places to mess up here. So you just want to be real careful there. Any questions to this point? Is everybody good? Okay. So then we're going to set the coefficients equal to each other. So like this polynomial over here is x squared plus 1. So this has to be x squared plus 1, which means a plus b has to be the coefficient of x squared over here. So a plus b is 1. There cannot be an x term because we want x squared in just 1. And so then that means that this coefficient needs to be 0. So we can go negative 18a minus 19b plus c equals 0. And then this constant term needs to be 1. So 81a plus 90b minus 10c equals 1. And so now we're going to go about trying to solve for A, B, and C. There's a few ways to do that. So you could use like what's called Gaussian elimination. If you study that, you may have done that in like algebra 3 or pre-calculus or somewhere, maybe algebra 2 even. But or you can just kind of mess around with this. What I'm going to do is just solve this one for A. And if I solve this for A, it's going to be in terms of B. And then I can plug that into these two, and that'll get these equations where they involve just B and C, and I can solve then from there. And so I can do A equal, or I'm sorry, I'm going to, yeah, A equals negative B plus 1. And then I'm going to sub that in for A on these two equations. So I'm going to get, for this one, I'm going to get negative 18 times negative b plus 1 minus 19b plus c equals 0. I'm going to simplify that down. So we get 18b, excuse me, 18b minus 18 minus 19b plus c equals 0. So 18b minus 19b, man, my fault. Negative b, we want to combine those. So negative b plus c equals 18. So if we simplify that down, we get negative b plus c equals 18. And now if I use this third equation and plug in the negative b plus 1 for A, then I get 81 times negative b plus 1 plus 90b minus 10c equals 1. Distribute this through, so we get negative 81b plus 81 plus 90b minus 10c equals 1. That gets us 9b minus 10c equals negative 81. And so combining those, we get 9b, negative 10c, and then, I'm sorry, negative 80, because we had a 1 over here, so negative 80. over here. So now I've got these two equations. So I've got this equation and this equation, and I'm going to use those two to try to solve for one of the variables. So what I'm going to do is quickly multiply this one by 10, because then the 10c and the negative 10c will cancel out. So I'm going to come over here and go negative 10b plus 10c equals 180, and then 9b minus 10c equals negative 80 from this equation. If I add those, I get negative b equals 100, and so b is 100. And now I can use that to go back and get a and c. So these numbers are kind of nasty, obviously, on this problem. But you go back now and just get a or c and a. So I've got negative b plus c equals 18.
Doesn't
so that
b
means
doesn't
that
b equal
from
negative
there
100?
negative 100 plus c is 18. So c is 118. And then from the very beginning, a plus b is 1. So a plus 100 is 1. So a is negative 99. And so then, okay, I've got a is negative 99, b is 100, and c is 118. So let's jot these down here. So a is negative 99, b is, my bad, b should have been negative 100, so my fault. Let's go back and fix that stuff. Right up here, my fault. So when I have negative b equals 100, b should have been negative 100. And so then that, let's just redo these two parts. So we've got, okay, so b is negative 100. That makes this negative 100 plus c equals 18. So then 100 plus c equals 18. And c is 80, yeah, 82. And then, okay, a plus b is 1. That's a plus negative 100 is 1. So then a is 101. My bad, guys. And if I made a small mistake like that before, yeah, and sorry, Andrew told me in chat and I did not see the chat, sorry. So yeah, so negative 100, that messes with these. If I made a small mistake before, let me know, but because of time, we may not go fix that. I think I'm good, but let's go back up here now. And so a is 101, my fault. And then b is negative 100 and c is 82. And now if we go back up here, then what that does is we can split this into 101 over x minus 10 plus negative 100 over x minus 9, and then 82 over x minus 9 squared dx. And now we split this into three integrals. So we're going to make it 101 integral 1 over x minus 10 dx minus 100 integral 1 over x minus 9 dx. And then I'm going to pull the 82 out and make this x minus 9 to the negative 2, because we're going to use the power rule. And yeah, we'll do 42 was next, and then we'll do 51 as well, Dominic. Okay, and so you bring that up and make it negative 2 because this is a power rule problem. So all of these are problems where we let u equal, like here, x minus 10, u is x minus 9 on this one, u is x minus 9 on this one, du is 1 dx in every case. So these two are just log of the bottom. This is a power rule where we would normally get like 1 over negative 1 u to the negative 1. But here we're going to get, we can go ahead and just kind of skip that and make it 1 over negative 1 x minus 9 to the negative 1 plus c. The other two are log form. So we get 101 natural log absolute value of x minus 10 minus 100 natural log absolute value of x minus 9, and then plus that last one. And now we simplify that last one and we get 101 natural log absolute value of x minus 10 minus 100 natural log absolute value of x minus 9 minus 82 over x minus 9 plus c. And that is the answer with these numbers. Hopefully you have nicer numbers, but that does work. Any questions on this? And like I said, if I did make a small computation mistake down here, I apologize for that. I think I'm good with these coefficients. But if, I did something like negative 100 somewhere else, it's going to throw those a little bit. So, but this is the process. So you solve for A, B, C. This one is obviously one of the more complicated system of equations to solve. But once you do, then you have two log forms and a power rule here. All right, any questions on 40 before we move on? We'll go to 42 next and then 51, just because those are the next two I got in chat. All right, so let's go to 42. So 42 is another system or partial fractions problem. I think it doesn't work out to be quite as bad at first, and then maybe the integral's harder, but let's see. So we got 42, and we got 5. The numbers I've got are 5x squared plus 2x minus 4 over x cubed plus 2x squared. Is this, I forget who asked, whoever asked this, Jacob, is this close enough to what you've got?
Yeah, it's pretty close. Just the coefficients are a little off, that's all.
I can't hear you, Jacob. I don't know if...
Can you hear me now?
Yeah, now I can.
Yeah, it's pretty similar, yeah.
Okay, yeah. I know it changes the numbers for everybody, but at least the process, and same with the first one, was it close enough to what you had?
Yeah.
Okay, hopefully you have better numbers than the one I got, but okay. This one, again, it's partial fractions because the denominator will factor and the degree of the top is 2, degree of the bottom is 3. So degree of the top is smaller than the bottom. So we can go and say, okay, 5x squared minus or plus 2x minus 4. And then the bottom, the way you factor that is you just take an x squared out. And so you get x squared times x plus 2. And so now the x squared on that is treated as a repeated linear factor. Oh, and I'm sorry, Nick, in the chat, can you talk about when you know you should try integration by parts? Yeah, let me look at that here in a minute with a couple examples maybe. These are not ones typically when you have a rational expression, so a polynomial over a polynomial, it's almost exclusively partial fraction. It's not always, but usually. So if it factors on the bottom and the degree of the top is smaller, then you're going to use partial fractions. So these aren't ones where you'd be considering integration by parts. Integration by parts is normally ones where U sub appears to work and maybe it doesn't, or problems where you wouldn't know what else to do. So like if you have a function just completely by itself, like inverse tangent x or natural log x, those are ones where when you try integration by parts, it happens to work. So I guess I kind of talked about that just now, but those are the ones that don't seem like it, but then ones where you have like two relatively unrelated functions multiplied, like e to the x times sine x, or x squared times log x, or x squared times cosine x, or something like that. Those are the normal places for integration by parts. There's always exceptions, but that's kind of the idea. Does that answer the question somewhat, Nick? Yeah, no problem. No problem. Okay, so and if there are any examples where you want to look at that, we can look at that in particular, but that's kind of the idea. So, all right, so this one though, everybody good picking out that this is probably partial fractions? Okay, so when we break this down, we do a over x, b over x squared, and then c over x plus 2. And the x squared, you don't do the ax plus b thing for that, because it's not an irreducible quadratic. Irreducible means there are no zeros. And so if you were to graph x squared, there is a 0. There's an x-intercept at 0. X-intercept and zeros are pretty much synonymous for quadratics. And so, or for any polynomial. But anyway, so you do this as a repeated linear. So you have it like it's x, but it's there twice. So a over x to the first, b over x squared. If it was x to the third, you'd have x, x squared, and x to the third as 3 separate fractions. So now you multiply by the common denominator, which is x squared times x plus 2 over 1. And when we do that, the left-hand side, the denominator cancels completely. And then on the right-hand side, that on the first one, one factor of x cancels. So you get a and then one factor of x, you get ax, and then x plus 2. On the middle one, x squared cancels, so you get b times x plus 2. And on the third one, the x plus 2 cancels, so you get cx squared, but that's it. And so now you distribute the ax and the b. So you get ax squared plus 2ax plus bx plus 2b plus cx squared. And now you combine terms again. So the x squared terms are a and c x squared. So we get ax squared and cx squared. And then the x terms are 2a plus b x. So we'll underline those in red. 2a plus bx. That's this one. And then the only constant term is the one that I didn't underline, which is 2b. So we got everything there. This one's not quite as bad at this stage. I think it's harder at the end. But now, okay, a plus c has to equal 5. 2a plus b has to equal 2. And 2b has to equal -4. Well, this is ideal because now b has to be -2. So we know immediately b is -2. We can plug that into this one now and get a. So we get 2a plus -2 equals 2. So we add 2 to both sides. And we get a is +2. And then we know that a plus c is 5. So 2 plus c is 5. So c is +3. So, okay, so we get 2 for a. And we'll write these in red. So it's something separate. So 2 for a, -2 for b, and 3 for c. And so now we go back up to this problem. And so then the first two are pretty straightforward. So let's just go ahead and write one step like this. So we get 2 over x, and then actually they're all pretty straightforward. My bad. I thought this one would be worse because of the way it looked, but it's not that bad. I was thinking it was x squared plus 2, but it's not. All right, so we get this. And now actually these are pretty straightforward. So you split this into 3 separate problems. So we get 2 integral 1 over x dx. But then when it's 1 over x squared, we want to think of that as x to the -2. And then on the last one, you pull the 3 out and you get 1 over x plus 2 dx. And so now this is 2 natural log absolute value of x. This is a power rule, so 1 over -1, x to the -1. And then the last one, technically use substitution, but du is 1 dx. And so then the only thing to do is simplify this. And so we get 2 natural log absolute value of x plus 2 over x plus 3 natural log absolute value of x plus 2 plus c, and that's the answer. All right, my bad. I was thinking this was going to be x squared plus 2. It was just x plus 2, so it's not as bad. If it was x squared plus 2, you'd have log and inverse tangent, and it'd be a little, it would be much worse. This is still a tough problem, but I thought it was going to take a lot longer. All right, are we good with this one? Any questions? Everybody good? All right, so next one is 51. Okay, so good. So 51 says, evaluate the following sum, n equals 1 to infinity, and I've got 1 over n times n plus 6. Is that close to what you guys have? Close enough? Okay. All right, so it says hint, rewrite this as a sum of partial fractions. So, okay, so let's do that in red because I'm not sure how much room this is going to take. So we're just going to go ahead and do the partial fractions part here, and then we'll do with the sum later. So the bottom is factored, and so we do a over n plus b over n plus 6. I kind of think this might take a while once we get done with this partial fraction part, but let's see. So we multiply by the common denominator, and we get 1 equals a times n plus 6 plus bn, and we distribute the a, so an plus 6a plus bn equals 1. And now we combine terms, so we get a plus b n plus 6a. So, okay, so a plus b is 0, and 6a is 1. Okay, so maybe not. So, okay, so a is 1/6, and then 1/6 plus b is 0, so b is negative 1/6. And so, okay, what that means is that this original sum, n equals 1 to infinity, can be rewritten as 1/6 over n plus negative 1/6 over n plus 6. And it's probably smart to move those 6's to the bottom and make it subtraction. So let's make it 1 over 6n minus 1 over, and then it's going to be 6n plus 36. So let's go with that. And now, okay, so the goal is to figure out the sum here. So it's not to prove that it converges. We know it converges, and we can tell that by a comparison test. Like if you distribute the bottom, you get n squared plus 6n, and we know that behaves like 1 over n squared. So anyway, so 1 over n squared would converge, so does the original by direct comparison. But we're actually trying to find the sum, and so the only ones we know how to find the sum of are geometric, telescoping, and then using Taylor series. And this it doesn't look like a Taylor series. It's not a geometric series. And so this hopefully is telescoping. And the idea is that it ends up being telescoping because these numbers are going to increase and eventually hit these numbers. And so a bunch of stuff's going to cancel. I think it's going to take a while. More than what we normally have done in class, but we want to find a formula for the partial sum. And so normally when I do examples, I use k in the problem and then call the partial sum Sn. Since they're using n in the problem, let's call the partial sum Sk. And so we start at n equals 1, and we increase n equals 1 to n equals 2 to n equals 3 until terms start to cancel out. So for n equals 1, we get 1 over 6 minus 1 over, and then 6 plus 36, so 42. And then for n equals 2, we get 1 over 12 minus, and then if we plug this in, we get 6 times 2, so 12 plus 36 is 48. And then for n equals 3, we get 1 over 18 minus, and then 18 plus 36 is 54. And if we notice what's happening, nothing's canceled yet. And like I said, normally the ones we've done, they cancel quicker than this, but the denominators are increasing by 6. So this is going 42, 48, 54. This is going 6, 12, 18. So this is going to get to 42. It's just going to take us a little bit. So what we normally do is we extend this until an entire term cancels out, which we should do. So we're going to go to n equals 4. That gets us 1 over 24 minus 1 over 60. N equals 5. Whoops. This one is n equals 4. Man, cannot write right now. So n equals 4, n equals 5. All right, so n equals 5 gets us 1 over 30 minus 1 over 66. Then we're going to get n equals 6 is 1 over 36. Minus 1 over 72, n equals 7 is 1 over 42 minus 1 over 78. Now the 1 over 42s have canceled finally, and then we're going to go one more at the beginning, at least. Not bad. We want to get one to cancel completely, so we're going to go a little bit further. Sorry, so we're going to get 1 over 48. You know what, we may stop early. But okay, 1 over 48 minus 1 over 84. And so 1 over 48 is going to cancel. Okay, so what I want to do, normally what we do, because this one's so long, I don't want to keep going until they cancel completely, but we want to figure out what's going to cancel. So 1 over 42 is canceling, 1 over 48 is canceling, 1 over 54 is canceling. So this is gonna cancel, this is gonna cancel, this is gonna cancel, and this is gonna cancel, but then so is 1 over 78. So this one is gonna be the first one where everything cancels, because these keep getting larger and are becoming these second terms. So then this 1 over 84 is also gonna cancel. Now at the end, then what's going to happen is we're going to go to n equals k. And normally we keep going backward because of time. I want to talk about, well, I do want to do it at least for a little bit. So let's go with n equals k. So remember, k we think of as being something very large, like a billion or something like that. And so when n is k, it's 1 over 6k minus 1 over 6k plus 36. And then we go back to n equals k minus 1. And so then, okay, if I go to k minus 1, I get 1 over 6n minus 6. And then I get 1 over 6n. It's 6n minus, like it'd be 6n minus 6 plus 36. So 6n plus 30. Now, what's going to happen is that a bunch of these are going to cancel as we continue back. But the leftover terms are going to be in the form or in the formula for SK. So SK is going to become 1/6 plus 1/12 plus 1 over 18 plus 1 over 24 plus 1 over 30 plus 1 over 36 plus, and then you would have to extend this backward, and I want to get to some more problems, so I don't want to keep doing that unless you guys really want to see it. I'm happy to do it. We could go, we'd have to go to like 6 back or 7 back. Yes, these should be k and not n, thanks. So 6k minus 6, 6k plus 30 on that one. But what's going to happen is the ones at the beginning of these are left over. The ones at the end of these are going to be left over. So like that's going to cancel. That's going to cancel. These aren't. And we're going to have 6 of them that are there. So we're going to have minus 6 fractions. So 4 that I'm not writing. And then minus 1 over 6k plus 30. And minus 1 over 6k plus 36. To do a formal proof, you'd need to write out all of those. But do you guys get the idea that why that's going to happen as we keep going back? Does everybody see what I'm talking about? Okay, so to find the sum, you're looking at the limit as k goes to infinity. Well, all 4 of these and these 2, the bottom goes to infinity. So these 6 all go to 0. So all of these go to 0. Man, make that actually a 0. That goes to 0. That goes to 0. So then the sum is the total of these 6 fractions. And so if it were me, you know, I would type in that on WebAssign or just do that on a calculator real quick. I know on a test you can't use a calculator, but you can type that in and it would take it. On a test you won't, or on the final, you won't have one where you're going to do 6 of them. But this is the idea. Does that make sense? Dominic, I know you're the one that asked that in particular. Do you follow that? Everybody, obviously, but does that make sense? So really, okay, cool. All right. Any questions on this or telescoping series in general?
Did you say that we shouldn't expect one like this lengthy on the final?
Correct.
Okay.
Okay. Yeah. You shouldn't, at least on the WebAssign part, like where you'd have to actually compute it. But WebAssign would take this, so I won't make a telescoping that's 6 where you have to go out 6 or 7 of them like that. All right. Other questions on this? All right. Other questions on the final period? I think I've gotten to everything in chat so far. Feel free to send something in chat or unmute yourself and you can say it out loud. Okay, power series problem, and then number 28. Yeah, so Andrew, there's a bunch of different power series types. And then we'll get to 28, Jordan. So power series types of problems, you need to be able to do these. So find the interval and radius of convergence. You need to be able to find a power series, a representation for a function using a over 1 minus r, using derivative or integral of that, using Taylor series, and then you need to be able, like, given another one, find a harder one, and then like maybe like evaluate an integral using these, or find the sum of a series using these. So somebody's saying 54, is that a power series question? No, okay, so 28 and 54 will be next. The recording this, I will try to post it tonight, Justin, no problem at all. If your internet's unstable, I was running late, I understand stuff like that happens. The harder ones, Andrew, so I don't know what the hardest ones are. Let me, I don't know what you guys think the hardest ones are. I think probably the hardest ones are actually the ones I focus on least. So I would, let's do these. And then if there's other ones you want to see, that's fine. Lynn, let me know. So let's find a power series for f of x equals 3x over 6 minus x. And you know what, let's make that 5x over 6 minus x. So we'll make it x squared too. So 5x over 6 minus x squared. Okay. And yeah, the derivative ones probably are the hardest. So if we want to do one of those in a minute, we can do that next. Keegan, you have to get 80% right in order to get the extra credit. I mean, you know, obviously try to do all of it for the final, but 80% is the cutoff. And however WebAssign scores that, I think it counts some of the ones with multiple answers a little bit higher than the others. It might be given 1 point per blank. I'm not sure, to be honest. But yeah, you have to just, yeah, but you could always work them again, I think, right? You can, but anyway, you should be able to work them a bunch. But yeah, 80% is the cutoff. All right, so find a power series for this. So this one looks like a over 1 minus r. Let me make this a little bit neater. So when that happens, you want to get it in the form a over 1 minus r. And so we need to factor the 6 out on the bottom. And so then we get 5x over 6 over 1 minus x squared over 6. And remember that ar to the k is equal to the sum k equals 0 to infinity. Man, a over 1 minus r is equal to the sum 0 to infinity of ar to the k. And so then, okay, that means that a is 5x over 6 and r is x squared over 6. So then, okay, this is the sum k equals 0 to infinity of ar to the k. So 5x over 6 over times x squared over 6 to the k power. Does that make sense? And now you simplify that. by raising everything to the k, so we get times x to the 2k over 6 to the k. And now to simplify that, we get k equals 0 to infinity, and then 5 over 6 to the k plus 1, and then x to the 2k plus 1, because you add the powers. And then that's it on this. If you needed the radius of convergence, I didn't ask for that, but if you did, then you would do absolute value of r is less than 1. So absolute value of x squared over 6 is less than 1. X squared is positive or 0, so we drop the absolute value, and now x is between negative square root of 6 and square root of 6. So the radius is square root of 6, and the interval of convergence is negative square root of 6, square root of 6. If you were asked for those, I did not ask for that here, but if you were, that's what you would do. Does that make sense? Does everybody follow that?
Do we have to show all that work when finding the radius?
No, you don't. No.
Okay.
Other questions? Okay. Okay, the derivative ones, Andrew, let's do one like that, and then we'll go to the two that people have listed in chat, the two specific numbers in chat. So find a power series for and let's say it's 7x to the third over 5 minus 2x to the fourth squared. And you know what? Let's make this something random. My fault. Let's make this 7x to the 8th. Okay, so find a power series for that, and so we'll call this f of x. Okay, so when you have the entire denominator squared, but other than that, it looks like a over 1 minus r. So this looks like a over 1 minus r, but the whole bottom is squared. Then this is the derivative of something that looks, or that is like a over 1 minus, man, cannot speak. This is the derivative of something that is in the form a over 1 minus r. And so what we want to do is we pick this other function g of x. And so g of x, there's a few ways to go about this, but what I would recommend that you do is when you have the bottom like this all squared, g of x is 1 over the bottom to the first. So I would recommend that you make it 1 over the bottom to the first power. So 1 over 5 minus 2x to the fourth. Does that make sense what I'm doing? Okay,
Why
now
are we able to do that?
So you pick this other function, and it's not that this is the same as this, it's that this is one we're able to get a series for. And now there's kind of 3 things we have to do. One thing we have to do is we have to get a series for this. The second thing we have to do is we have to figure out what exactly is the relationship between f of x and g of x. It's not, because I made the top one, it's not like the derivative of this is actually equal to this. We need to figure out what the exact relationship is. And then we need to use that relationship to get the series for f of x. So let's do all 3 of those, and then we'll kind of outline and recap what we're doing. So we're going to go ahead and get a series for g of x. So that means we need to factor the 5 out, so that this is exactly in the form a over 1 minus r. So a is 1/5, r is 2/5 x to the fourth. And so, okay, if we raise everything there to the k, we get 2 to the k on top. We get 5 to the k plus 1, and then x to the 4k. So the 5 to the k plus 1 is doing 5 to the k here times the 5 to the first here. Does that make sense to everybody? Now, this is the series for this other function that we made up. So what we want to do next is we want to figure out, okay, what is the relationship between this function and f of x? So the derivative of this involves this squared in the bottom. So what I'm going to do is I'm going to come over here and say, okay, g of x is 1 over 5 minus 2x to the fourth. I'm going to think of that as 5 minus 2x to the fourth to the negative 1. And now I'm going to take the derivative of that. So we get times negative 8x cubed because of the chain rule. And then the derivative then simplifies to positive 8x cubed over 5 minus 2x to the fourth squared. Does that make sense to everybody, what I'm doing here? And we'll talk about why I'm doing it in a minute, but do we understand how I got the derivative of this? Everybody good? And I'm sorry, it's a little illegible. This is negative 8x cubed over here. So the negative 1 times negative 8 is positive 8. That's where I'm getting that. Okay, so we have a series for g of x. We know how to take the derivative of this series. So if we were to take the derivative of this series, we would then have a series for this function that I've got in green. So we want a relationship between f of x and g of x. We want a series for this. Well, the green function is close to this, but it's not exactly the same. So what we do is we say, okay, well, f of x then is close to g prime of x, but it's not the same. Instead of, I want the denominator to be the same, but instead of 8x to the third, I want 7x to the 8th. So I want to get rid of the 8 and end up with a 7. So I multiply by 7 over 8 because the 8 in the bottom will cancel that, and the 7 in the top will get me this. And then I want to go from x to the third to x to the 8th. So I multiply by x to the 5, because when you multiply powers, you add them. And so 7 or x to the 5th times x to the third will get me x to the 8th. Does that make sense to everybody? Okay. All right. So then the idea is, okay, we've got this series for g of x. Because of what the derivative of g is, then f of x is 7/8 x to the 5th times the derivative of g. So what we need to do is we need to take the derivative of the series in red and then multiply that by 7/8 x to the 5th, and that will get us a series for f. So we're going to say, okay, then this is equal to 7/8 x to the 5th times the derivative of the sum that we found for g of x, the red one, the sum k equals 0 to infinity, 2 to the k over 5 to the k plus 1, x to the 4k. So then it's 7/8 x to the 5th times, and now derivatives are actually straightforward. They look really hard, but you just do the power rule. This is a constant, so you bring this down. If this was like x to the 40 instead of 4k, if it was x to the 40, it'd be 40 x to the 39. And so what you do is you bring the 4k down, it gets multiplied on the top of the fraction. So instead of 40, it's 4k. And then instead of 39, it's 4k minus 1, because that's how you subtract powers. Does that make sense? So this is, even though this looks incredibly complicated, all we're doing there is the power rule. You bring the power down and subtract 1 from it to take the derivative. Now, several things that can happen, but one thing that has to happen. One is we need to put this into our summation. So 7/8 gets multiplied in here. So we're going to multiply the 7 on top of that fraction and the 8 on bottom of the fraction. So we're going to get 2 to the k times 4k times 7 over 8 times 5 to the k plus 1. And then x to the 5, you multiply with x to the 4k minus 1. So you add powers. Well, 4k minus 1 plus 5 is 4k plus 4. And so we get it to here. And now this is the first really acceptable answer. You can simplify a little bit. So you could cancel the 4 with the 8 and get a 2. And then you can subtract these exponents and get 2 to the k minus 1 on top. You can also then make it, okay, 7k over 5 to the k plus 1, x to the 4k plus 4. You can, but don't need to, change the sum to start at k equals 1. Again, that's not necessary. You can leave it as k equals 0. If you plug 0 in, you get 0 for the whole term because of this k here. So if you wanted to increment the sum, you can. A lot of textbooks do this, where when you take the derivative, you jump up on the k value because usually that first term in the derivative is 0. So this is probably the most simplified you could do. If you do any version of that, that's fine. So if you put this, that would be okay. If you put this where it starts at k equals 0, that'd be okay. Or if you had 2 to the k over 2, that'd be okay. So any form of these last two answers would be okay. And I think Andrew's saying that he wanted to do the hardest one. I think the derivative ones probably are the hardest ones, not because the derivative is that hard over here. Like doing this derivative is pretty easy, but it's this part and this part that is really challenging sometimes. So that's why I would consistently go with 1 here. And so somebody's saying, why can we do that? Well, we can't really, but you're just making up this other function. So you're saying, okay, well, g of x is this, and then I'll figure out later how to get this back to this original. So you get the series for g of x, you figure, okay, well, the derivative of this is at least close to this because it's going to have the 5 minus 2x to the 4th squared in the bottom. The numerator is not the same, but then that's where we get this to kind of take care of that. Okay, so the question in chat, to find the interval and radius convergence, would you do the ratio test of the answer? You don't need to do that. To find the radius of convergence, so the theorem we're using says that when you do the derivative, the radius of convergence stays the same. So the radius of convergence we could figure out, and we'll do this in a completely different color in purple. We can figure out that, okay, the radius of convergence is when absolute value of r is less than 1. So then the absolute value of 2/5 x to the 4th is less than 1. And then you can do some steps to figure out, okay, well, it's negative 4th root of 5/2 is less than x is less than the 4th root of 5/2. So the radius of convergence is the 4th root of 5/2. That doesn't change. Whether the endpoints are included can change. So like the endpoints are not included for this one. So this is on negative 4th root of 5/2, comma 4th root of 5/2. So they're not included for the red one, but when you take the derivative or integral, that can change. And so if you wanted the interval, you should test the endpoints. I think typically, when you take the derivative, you would never like pick up an endpoint, but I actually don't know that for sure. I would have to do a little more research. I've not studied the theory on this in quite some time, but the endpoints could change, like whether they're included or not could change. So you would test the endpoints, but you would not need to do the whole ratio test. Does that make sense, Andrew? Okay. Other questions? This is tough and very involved. I understand that. I don't have anything else helpful to say about that. It is tough. Sorry. This is not an easy type problem. The lecture on this would have been the last lecture before Thanksgiving. So if you guys want to go back and watch that, or no, that's not true. The last lecture of the week before Thanksgiving. So not the Monday, Tuesday of Thanksgiving week, but right before that, probably the Thursday before Thanksgiving. Okay.
Can you explain the endpoints again and how to find the intervals?
Yeah, so if you were asked for that, whenever you use, okay. So for the interval radius convergence, the normal way to do it is to use the ratio test. When you've used A over 1 minus R, you don't need to use the ratio test because you know that it converges when this is true, when the absolute value of R is less than 1. Does that make sense?
Yeah.
Then okay. So on the red series, the interval of convergence is negative 4th root of 5 halves to positive 4th root of 5 halves. And when you're using this, the endpoints are for sure not included. When you use the ratio test, you have to independently test endpoints. But when you're using this, they're not included. When you take the derivative or when you take the integral of a series, the radius of convergence does not change. So the radius is still this, but whether the endpoints are included or not can change when you take the derivative or integral. So this is not included on the original, but when you take the derivative, it might then be included. And so if you wanted the interval of convergence, you would need to independently test these two on this series. Does that make sense?
Yeah, kind of.
Okay, we're not trying to get to that level of complexity. So if you're doing this, I would typically just ask for the radius convergence, if anything. So then the idea is this would be the radius once you're here. But like basically the interval is just maybe you would have a bracket now, and maybe you'd have a bracket here now. Probably not, but maybe. And so you'd have to like plug those in and test this and figure out whether it converged or not. Not something I'm worried about you actually doing. Does that make sense?
Yeah.
Okay.
Thank you.
Yeah, no problem. Other questions on this, guys, because I know this is really complicated. We've not had a test on it yet at all. All right. Okay, now I think there were two other questions asked, 28 and 54, that I think we haven't done, or at least we haven't done today. I don't think we've done them at all, but let's go back to 28 and then we'll do 54. Oh man, and then we've got 10 minutes. So this might be it. 28. Okay, yeah. All right, so this is what I've got. I think the only thing that changes from one problem to the next is whether this is a 5 or some other constant. So, okay, so this is a definite integral. So you want to go, or what I would recommend you do is go over to the side and do the indefinite integral, so the antiderivative, without the bounds on there at all, and just do this however you do it. So in this case, it's even powers of sine and cosine. So you want to use the half angle formula. Half angle formula for sine is sine squared of 2x is 1/2 times 1 plus cosine of 2x. I'm sorry, minus, plus cosine minus for sine. And so then we get 5 times 1/2 integral 1 minus cosine of 4 theta d theta, because the way this works is, I'm struggling. This is sine squared x equals this. And so whatever is here, it's then doubled here. So when there's 2 theta here already, it's 4 theta over here. And so now we distribute the 5 halves and separate this into 2 integrals. So we get 5 halves theta, and then 5 halves, and then this is a quick U substitution where we get 1/4 sine of 4 theta plus c. We're not quite done, but with this part, but does that make sense, everybody? All right,
Can you
so
do
I
the
would,
use slip real quick?
yeah, sure. So on this second part, so it would just be like integral of cosine 4 theta d theta. So u would equal 4 theta. Whoops. U equals 4 theta. Du is 4 d theta. So you multiply inside by 4 and outside by 1/4. So then it's 1/4 integral cosine u du, which is 1/4 sine u. Does that make sense?
Yeah.
Okay, cool. All right, so that's where we get this. And so then I would multiply those fractions together. And now, okay, so the,
Shouldn't the derivative of cosine be negative sine?
it's the antiderivative. So antiderivative, you're good. Antiderivative cosine positive sine. All good. Other questions? Okay, so we go back over to the original problem and we just say, okay, well, then this is equal to that antiderivative. Evaluated from 0 to pi over 2. And so you plug in pi over 2 for all the thetas. And then plug in 0 for all the thetas. So then this is 5 pi over 4 minus 5/8 sine of 2 pi. And then minus 0. Always double check that. It is not always 0 here, but 5/2 times 0 is 0. Sine of 0 is 0. And then sine of 2 pi is also 0. So this simplifies to 5 pi over 4. And that's it. Does that make sense to everybody? Any questions? Okay. So that's 28. And then 54 is also a question in chat. 54 is, okay, find the sum. Okay, find the sum of this series. So 54 is the sum n equals 0 to infinity of 7 plus 2 to the n over 4 to the n. And this is, it says use the formula for the sum of a geometric series to find the sum or state that the series diverges. Okay, so this one does not diverge. You can rewrite it as the sum n equals 0 to infinity of 7 times 1/4 to the n plus the sum n equals 0 to infinity of 2/4 to the n. And so that works differently because this is to the n and this 7's not. And so this, the 7 comes out and it's 1 to the n over 4 to the n. This one is 2 to the n over 4 to the n. So we get this. And then you can simplify 2/4 obviously to 1/2, which is probably easier when you're doing these summations. And now both of these converge and it's a over 1 minus r. The sum is a over 1 minus r. So we get a is what you get when you plug in this first value. So we get 7 times 1/4 is 0. So it's just 7 over 1 minus r. So 1 minus 1/4 plus, and then a is again what you get when you plug in 0. So, or plug in this first value. So that's 1 and then 1 minus 1/2 on the bottom. So we get 7 over 3/4 plus 1 over 1/2. That's 7/1 times 4/3 plus 1/1 times 2/1. That's 28/3 plus 2. And that's 34/3. But WebAssign will probably take a less simplified answer. Okay. So that's all we're gonna have time for today, guys. I'm sorry I was about 5 minutes late at the beginning. I'm happy to meet tomorrow at 12:30 if people want to do that. So even if just one or two of you want to do that, let me know, and we will meet tomorrow at 12:30. Just type in chat yes, or unmute yourself and tell me you want to come. If not, we will wait until Sunday at 3. Okay, then we'll do 12:30 tomorrow, probably just for an hour. So we'll do 12:30 to 1:30 tomorrow, and then Sunday 3 to 5. So we're going to do Friday 12:30 to 1:30, and then Sunday 3 to 5, and just on Zoom. Sunday, I'm going to open up to every Math 156 section, or at least I'm going to tell the other instructors, and they're welcome to tell their students. That will be question and answer, can be from the review, or can be from the bonus, but could be from anything. And then tomorrow, we'll try to focus mostly on the bonus again. All right, that's it for today, you guys. Thanks for coming, and I hope I'll see you tomorrow. Thanks.